next speaker is Yandi Wu from University of Wisconsin, and she's going to speak a little bit about marked length spectrum rigidity of certain quotients of the Davis complex.
Great. Yeah, thank you so much, Frank, for organizing this conference and for the invitation. Thanks everyone for coming. Yeah, and as Frank mentioned, I'm going to be talking about marked length spectrum rigidity today. So I'll kind of motivate that first. So this is the motivation. So Mostow rigidity is what I want to start with. So this is kind of a geometric form of Mostow rigidity that's like stated here. So Mostow rigidity basically says that if two closed hyperbolic M manifolds for a dimension of the manifold is greater than 2, then if your two manifolds have the same isomorphic fundamental groups, then they're actually isometric. So this is kind of a very strong form of rigidity because you have topological information that's kind of implying information about the metric, which is very surprising. And some remarks here is that, first of all, Mostow rigidity does not hold for surfaces. So this is kind of a result of technior theory. So if you know any technior theory, you might know that there's a whole technior space worth of metrics that you can put on a surface, on a hyperbolic surface. So hyperbolic means constant curvature -1. And also if you have variable negative curvature, then you actually need more conditions, and Mostow does not hold. So you might wonder, okay, Mostow is kind of a strong statement. It only works for these hyperbolic M manifolds where n is greater than 2. Is there some form of rigidity that's true for surfaces and for variable negative curvature? And that's kind of where marked length spectrum rigidity comes in. So let me just define that for you. So first you need to define the marked length spectrum of a metric space. So the marked length spectrum of a metric space is basically a function from the pi1 of your metric space to the positive reals. And it assigns a length to each homotopy class. So more specifically, it assigns the infimum of lengths of curves in your homotopy class to the homotopy class. So in particular, if your metric is negatively curved or cat -1, then the marked length spectrum actually boils down to assigning a length to each closed geodesic in your metric space, because each element of the fundamental group for negatively curved metrics has a unique geodesic representative. So you can think of it as a length assignment to closed geodesics in your space if your space is negatively curved. And then we say that a collection of metric spaces is marked length spectrum rigid if whenever you have two metric spaces with the same marked length spectrum, then they're actually also isometric. So I want to point out that implicit in this definition of marked length spectrum rigidity is that the fundamental groups of your two spaces are the same, because there's no way to compare their marked length spectra if they have different fundamental groups. So that's why it's sort of like a weakening of Mostow rigidity, because remember Mostow said that if the fundamental groups are the same, then the two spaces are isometric. But here you have this additional assumption that the marked length spectrum is also the same. So that's kind of an introduction to what marked length spectrum rigidity is. And you might be wondering, so what are some examples of these spaces? And remember that Mostow wasn't true for surfaces, but surfaces have been shown to be marked length spectrum rigid. So first of all, hyperbolic closed surfaces are marked length spectrum rigid. So this is a result of Fricke and Klein from 1965. And the thing I want to mention is that there's even a stronger statement of this, which is that you actually only need to know the lengths of finitely many closed geodesics to determine the metric for hyperbolic closed surfaces. So these are very much marked length spectrum rigid. And then there's a result independently proven by Otal and Crook from 1990, which states that negatively curved Riemannian closed surfaces with like variable negative curvature are also marked length spectrum rigid. And that kind of inspired a whole list of generalizations So first of all, Croak-Fethy and Feldman generalized Crook's result from 1990 to show that non-positively curved Riemannian closed surfaces are actually also Mark-length spectrum rigid. And then Hersonsky and Paulin started including some cone singularities in the metric. So they showed that negatively curved surfaces of cone singularities, finitely many, are Mark-length spectrum rigid. And then there's some generalizations to flat metrics as well. So this is work by Dushin, Leininger, Rafi, and also Bankovic and Leininger. And then I think the most general result that I know for surfaces is that non-positively curved surfaces with finitely many cone singularities are Mark-length spectrum rigid. So that was shown by Constantine in 2018. So that's like all these examples for surfaces. And you might wonder, okay, Mostow also didn't hold for variable negative curvature of n manifolds in general. So that's actually, you might wonder, okay, is there like a Mark-length spectrum rigidity result for that? That's actually a wide open question. So this is a conjecture by Burns and Katak from 1985. So they conjecture that all closed negatively curved Riemannian n manifolds of all dimensions are actually Mark-length spectrum rigid. So as you can see, this has been shown for surfaces, but for other dimensions, except for maybe dimension 1, it's wide open. So yeah, that's just, if you want to think about that problem and you solve it, you'll probably be really famous. So yeah. And you might wonder, okay, what about Mark-length spectrum rigidity for like other spaces that are not manifolds? So that's kind of what I'm studying. So I study these objects called p-manifolds, which behave kind of similarly to surfaces, but they're not quite surfaces. So this was actually a term that was coined by John Lafont during his thesis work in 2007. And the P stands for piecewise. So these kind of have piecewise Riemannian metrics on them, and they're like piecewise manifolds. So I'll just define the two-dimensional version for you. So these are constructed by gluing together surfaces of boundary, which are called chambers, so that each boundary component is glued to at least one other boundary component. So you have an example here where I have a collection of surfaces of boundary, and then all of the boundary components are kind of identified to at least one other boundary component. And you get this like surface amalgam, or this p-manifold. And again, this is like no longer a manifold, but it looks a lot like a surface. And yeah, and one thing that I also want to mention is that I actually don't want the gluing curves to intersect. So this was actually a condition that was imposed by Lafont when he originally defined these objects. So it's like a simplifying condition for now, but I think in the future I could probably work with these. So yeah, so this is sort of the object that I'm studying. And this is kind of like a very broad definition. So I do need some additional assumptions here. So first of all, I actually want my gluing curves to be simple closed curves and a totally geodesic subspace in my p-manifold. So I think this is actually a natural condition to impose, because if I impose this condition, then I actually get a lot of nice properties for my p-manifold. So first of all, my p-manifold is going to be Gromov hyperbolic and also cat -1 if I impose this like simple condition. So that's like, those are all good things to have. And then the other natural condition is that you have all these like negatively curved, you have all these results for Mark-length spectrum rigidity for negatively curved surfaces. So maybe you want some like negative curvature on these p-manifolds. And that's like kind of the second condition, which is that each chamber has to come equipped with a negatively curved Riemannian metric. And the reason again for that is negative curvature is just like nice to work with when you're doing Mark-length spectrum rigidity. So those are just two additional assumptions, and we call a p-manifold satisfying those assumptions a two-dimensional simple negatively curved Riemannian p-manifold. So that's kind of a mouthful, but that's what I'm studying. And as I'll talk about later, these are actually the quotients of the Davis orbit complex. Yeah, so now I want to sort of state my theorem because I've defined my objects and I've defined Mark length spectrum rigidity. So I basically prove that if you have two-dimensional simple Riemannian negatively curved P manifolds with the same Mark length spectrum, then they're actually isometric. So notice that these P manifolds are actually the same space topologically now. That's like an assumption that I've imposed. So I actually show something a bit stronger, which is that this isometry is actually isotopic to the identity. So if you're more familiar with like how techmuir space is defined, you can think of this as saying like G1 and G2 are like isotopic metrics. So they're equivalent up to isotopy in the space of metrics in these P manifolds. And yeah, so just to give you a flavor of how my proof goes. So first of all, the first step is to kind of prove the space case, which is prove the conjecture, or I guess now it's like prove the theorem, not conjecture, is true if every chamber in my P manifold can be included into a closed surface. And then the second step is kind of like more geometric group theoretic in like, it's kind of got this, it uses these techniques that's common in like GGT. So I construct finite Shia covers and I use this, like, I also construct these like doubles of P manifolds to reduce to the base case. So I'll kind of like go over some specifics of that later on, but I just wanted to sort of give you an idea of how this is done. So yeah, so now I want to sort of take a quick break from this and justify my invitation to this geometric group theory conference by sort of explaining the connection there is with like right angle Coxeter groups and how these P manifolds have been used in geometric group theory. So yeah, so this is sort of a refresher if you're not familiar with right angle Coxeter groups or you just like don't remember the definition. A right angle Coxeter group is very widely studied in geometric group theory. It's a group of really nice properties, but it's defined using a simplicial graph. And the graph gives you this group presentation. So all of the generators in the right angle Coxeter group are vertices in your graph. The vertices have order 2, so every generator has order 2. And also there's a relation between two generators if there's an edge between them in the graph. So in particular, they actually commute if there's an edge between them. So there's some examples here. So if you just have a graph with 2 vertices, there's no commuting relations because there's no edges in this graph. So the only relation you have is that all the generators are order 2. So the resulting right angle Coxeter group is a free product of Z mod 2Zs. And then kind of on the opposite end of the spectrum, if you have a complete graph on 4 vertices, then every single generator commutes. So you actually get an abelian group. But the generators are still order 2. So the resulting right angle Coxeter group is like 4 copies of Z mod 2Z. And yeah, so that's like sort of a quick refresher on right angle Coxeter groups. And I want to sort of introduce a Kg1 space for these groups. So a Kg1 space, remember, is like, it's a space that has the property that the pi1 of the space is the group. So the pi1 of these Davis orbit complexes is actually the right angle Coxeter group. And yeah, so the way that you construct these, at least for 2-dimensional right angle Coxeter groups, is that you can think of them as like quotients of the Davis complex. So in other words, like you take the Cayley graph of your right angle Coxeter group, and then that Cayley graph will have a lot of squares and rectangles, or squares that kind of represent commuting relationships. So whenever you see a square, you kind of fill that in with a 2-cell. And you take the quotient of that filled in Cayley graph by the right angle Coxeter group, and you end up with the Davis-Orba complex. So I've kind of drawn like this this action on the Davis-Orba complex here. So if you quotient by the right angle Coxeter group, you get this like collection of orbifolds glued together, and that's why it's called an Orba complex. And the way that I've drawn it here, it has sort of like a Cat0 geometry, but you can put like a hyperbolic metric on it, and maybe it'll look something like this like orbit complex that I've drawn on the bottom here. So if I put a hyperbolic metric on my Davis-Orba complex, I can actually construct a finite Shia cover of this Davis-Orba complex that's a p-manifold. In some cases, it hasn't been shown for like every single Davis-Orba complex. But here I have a force Shia cover of a Davis-Orba complex that's a p-manifold, for example. And this is actually a orbifold cover, but there's still sort of a subgroup correspondence here. So there's like the fundamental group of this p-manifold is actually a finite index subgroup of my right angle Coxeter group. And as a result, these like p-manifolds have been used for the commensurability classification of certain right angle Coxeter groups. So if you're curious about that, I would recommend reading this very nicely written paper by Danny Stark and Thomas from 2017. Yeah, so that's kind of the connection to geometric group theory, because commensurability classification is like something that people in GGT really care about. So that was kind of like my 5-minute justification for why this is related to geometric group theory. So yeah, yeah, there's a connection to right angle Coxeter groups here. And hopefully in the future, I can sort of like use this connection. Since I'm familiar with p-manifolds, maybe I can use this connection to explore right angle Coxeter groups a bit more. Yeah, but kind of going back to the proof of my theorem though, I don't really use any of this, but as I stated before, I have these 2 steps. So first of all, there's like the space case where I prove the result, the Marshalling spectrum rigidity result for these p-manifolds where every chamber can be included into a closed surface. So here's an example where that's true. So I have this p-manifold with 3 tori with a single boundary component glued together. And then notice that each torus can kind of be included into a genus 2 surface. So this kind of falls into the base case. And the idea here is that Otal has these isometries between closed surfaces. So there's an isometry between the red genus 2 surfaces, and there's an isometry between these blue genus 2 surfaces. So I want to sort of show that Otal's isometries agree on the intersection of the 2 genus 2 surfaces. And that allows me to patch the isometries together to make a global isometry. So that's kind of the idea behind the proof. And showing that these isometries are compatible, that's the hardest part here. And yeah, I don't think I'll say much more about like how I show that, but I do want to sort of illustrate how the isometry is constructed. So first we can sort of revisit Otal's isometry here. So he constructs the isometry by taking universal covers. So remember that Otal works with closed surfaces, and the universal cover of a closed surface is just a disk. So what he does is that, okay, so first of all, by the fundamental theorem of geometric group theory, there's actually a quasi-isometry between the universal covers of your 2 surfaces. And then he kind of constructs this map using this like boundary homeomorphism that's induced by the quasi-isometry. So quasi-isometry induces a boundary homeomorphism, and that homeomorphism determines where geodesics are mapped. Because if you have a geodesic in your universal cover, your boundary homeomorphism maps the endpoints to sort of like points on the boundary of your other copy of the universal cover. And then since you have negative curvature, there's a unique geodesic between these endpoints. So he shows that if you have a point in your surface and you lift that to some point in your universal cover, you can consider all the geodesics in your universal cover that pass through that point. And then they get mapped via the boundary homeomorphism to a set of geodesics in the other copy of the universal cover. And Otal actually shows that those geodesics actually all intersect at a single point, which is pretty amazing if you think about it, because there is a guarantee that these geodesics will pairwise intersect, but there's really no guarantee that they intersect at a single point. So that's like highly non-trivial. I mean, it's an annals paper, so it was kind of a big deal when he proved this. And then he shows that point, that sort of like, you can map that point of intersection in your original universal cover to your new point of intersection in the other universal cover. And that map is actually a Pi1 equivariant isometry. So you can kind of project back downstairs to make an isometry between closed surfaces. So that's the idea. It's induced by this boundary homeomorphism. And then the way that it works for p-manifolds is that it's kind of similar, except that your universal cover is a lot more complicated. So now I have a collection of sort of half planes glued together in a tree-like fashion, but you can sort of do the same thing. You take a point on your p-manifold, lift your complicated looking universal cover, consider all the geodesics that intersect at that point in your universal cover, and then those geodesics will get mapped via the boundary homeomorphism to a set of intersecting geodesics in your other copy of the universal cover, and then you project back down. So this is like very much similar to what Otal did. So that's kind of like how the isometry works for the base case. Yeah, and then I just want to sort of briefly touch upon how the covering argument works. So the rest of the proof is devoted to reducing to the base case. So for example, I have this p-manifold here on the left-hand side that consists of a genus 2 surface with a torus of a boundary component attached to it. And that torus of a boundary component can't be included into any closed surfaces. But if you construct a two-sheeted cover, then you actually get this new p-manifold on the right-hand side, where like now you have two copies of your torus with a single boundary component, and now each of those can be included into a genus 3 surface. So now I've reduced my p-manifold to a problem for the base case. And yeah, so that's kind of like how the covering construction, that's the idea behind the covering construction. And I just included some slides to show that this got a little bit complicated. It's like kind of hard to generalize because, you know, there's like so many different kinds of p-manifolds that can arise. It's like every time I sort of thought I proved it, there is a new counterexample. So that was kind of a mess. And that's why you need a doubling argument as well. So this is like the double of a p-manifold is kind of, the idea comes from doubling a surface. So you take two copies of each of the chambers in your p-manifold and you glue all of those chambers together. So I have like an illustration here where my d of x, which is my double of my p-manifold, consists of like twice as many chambers as like my original p-manifold. And yeah, so that's like the idea. And now you can see that you can just pair each chamber with its double. If you pair a chamber with its double, then you get a closed surface. So we've reduced to the base case once again. And I just want to sort of present the key difficulty here with the doubling argument, which is that you need to show in order to reduce the base case that if you have two p-manifolds with the same Mark length spectrum, then their doubles also have the same Mark length spectrum. And that's actually that's not trivial because the Mark length spectrum of the double has a lot more data than the Mark length spectrum of the undoubled p-manifold. So for example, I have this like very badly drawn diagram here where I have this like red closed geodesic. So the length of that red geodesic is part of the Mark length spectrum of my double, but I can't really recover that length from the Mark length spectrum of my original p-manifold. So I have to figure out how to do that somehow. And I'll just say the main tools were geodesic currents. So if you're curious about those, I can talk more later. But yeah, I just wanted to end on that because I think I'm out of time. Yeah, thank you everyone for coming. Thanks, Frank, for organizing. And let me know if you have any questions.
All right. Thank you very much. I think you guys saw some things in there. All right. Anybody have any questions? You can unmute yourself. Something in the chat. Can you speak any more about the currents for a minute, for the geodesic currents?
Yeah, I can try. So these are basically measures, like it's a fancy name for measures on unoriented, unparameterized geodesics in the universal cover. That's all they are. There's some extra conditions on them, but they're really handy because there's a very special type of current called the Liouville current, which allows you to recover lengths of closed geodesics. So yeah, I don't know if I want to go any more deeper than that, but let me know if you are curious. But yeah.
Well, let's thank Yandi again.